Okay, welcome to page 5 of the Physics for Space Travel. I'm going to take you through the orbital mechanics part of this book. This is for students as well as teachers who want to teach the subject. So here is the introduction. I would recommend you read it, but I am not going to go through it. Okay, here's the table of contents. So for orbital mechanics, here we have it. Okay, we're not going to cover model rocket design and launch in this video. Okay, the first several pages provide a summary of the essential physics you must know to understand orbital mechanics. If you've covered this material with your teacher, then you can skip this section. If it's been a while since you've covered classical mechanics concepts, then I would recommend reviewing this information prior to moving on to orbital mechanics. Okay, so here's page 1 of the orbital mechanics part. It's on page 24 of the book. Okay, so assumptions I've made in this book and in the Orbiter 2016 defaults. They are simplifying assumptions, and they include Earth is a perfect sphere of uniform density. Atmospheric drag is ignored. It is present for low Earth orbits in tiny amounts, non-existent in most other orbits. Radiation pressure is ignored. Radiation pressure due primarily to the sun is very tiny. The loss in computation precision by making such assumptions is negligible. The factors above can be modeled in the Orbiter 2016 software. You can look at the parameters from the main menu. However, they have been turned off so that the computations made by the reader of this book tie to the DG's MFDs. So I would recommend any reader turn those parameters off in the Orbiter simulator. To do orbital mechanics, we must first define a coordinate system. For objects orbiting the Earth, we will use the geocentric equatorial coordinate system. Details include the origin of the coordinate system is at the center of the Earth, right here. The x-axis points in the direction of the vernal equinox. That's the direction of the sun relative to Earth on March 20th. It's labeled I here. The z-axis points in the direction of the North Pole. It's labeled K here. The y-axis is perpendicular to both z and x axes, labeled J here. The xy plane, right here, is the plane of the equator. Imagine a sheet slicing through the equator, and that's the xy plane. For objects orbiting the sun, the coordinate system used is the heliocentric, whose origin is the center of the sun. So why do objects orbit a central mass? Okay, the girl to the right here is causing a ball, okay, to orbit or circle about her. She does this by providing the ball with an initial velocity and maintaining tension in the string. Tension is a force, and in this example, the force is directed from the ball, from here, towards the girl. Such a force is called centripetal force, which causes a centripetal acceleration, so towards the center. So that here you have it. For an object to orbit a central mass, all that is required is an initial velocity and a central force. The centripetal force that provides for the orbital motion of the Delta glider around the Earth, or any satellite or object around the Earth, is the gravitational force between the Delta glider and the Earth. So in this diagram, the Delta glider is the red oval-shaped object, and the Earth is a solid blue circle. The direction of the gravitational force is directly between the DG and Earth, Delta glider and Earth. So here's the direction of the gravitational force. This direction is referred to as a radial direction. Okay, it's between the two objects. So gravity is a field force versus a contact force, meaning there's no physical contact between the interacting masses. The magnitude of the gravitational force between the Delta glider and the Earth is given by this equation here. So this would be the mass of the Delta glider. This is the mass of the Earth. G is a constant divided by the distance between them squared. And the distance r here is from the Delta glider to the center of Earth, not the surface of the Earth. Okay, for the acceleration due to gravity, just divide this equation by the mass of the Delta glider, and this would be its acceleration. Here's an example. Okay, if the mass of Earth is 5.98 times 10 to the 24th, g is always 6.67 times 10 to the minus 11, and r is equal to 6.38 times 10 to the 6, the acceleration due to gravity is 9.799 meters per second squared. So try the exercises as you work your way through the book. The answers to the exercises are available in a teacher's manual. So here's another exercise you can try. The question here is, what's the force at this location here? Okay, so you have to incorporate the force at this location due to Earth, the force at this location due to the moon, and the force at this location due to the sun. So you would apply this 3 different times. For this calculation, it would be in the plus direction. For these 2 calculations, it would be in the negative direction, and you just add them all up. Okay, so previously I talked about the gravitational force. So again, the gravitational force direction is between the delta glider and Earth. Then you also have something called the prograde thrust. Okay, so when you provide a thrust to delta glider, it will be in this direction, in the direction of travel. And a retrograde thrust is at 180 degrees to that, so it's in the opposite direction. Okay, so this is really interesting. Richard Feynman, probably one of the top 5 physicists of all time, came up with this way of looking at an orbit and really simplifies as to what an orbit really is. So say you've got a satellite here, and say the acceleration due to gravity using the previous equation is 0.223 meters per second squared. So in 1 second, okay, this thing is falling towards the Earth, okay, and in 1 second it's going to fall at this acceleration. Okay, and this is the time, 1 second squared times 1/2. So in 1 second, it'll accelerate this distance right here, 0.112 meters. So if you want this thing to stay in a circular orbit, it's got to travel this distance, x, in the same amount of time that it traveled from here to here to stay at this location here, again, in orbit, in a constant circular orbit. Okay, so Richard Feynman came up with this wonderful equation, this x here, is equal to 2 times this r, okay, the distance from Earth to the satellite, times s, square root. So when you compute that, you get 3078 meters, okay? So it travels 0.112 meters in this direction, but it must travel 3078 meters in this direction, right, to stay on the orbit. And let's do that in 1 second. Okay, so what's the velocity of this thing to maintain a circular orbit? It's 3078 meters per second. This is less than 0.2 of 1% difference from the speed computed for circular orbit using more traditional methods, which we'll do here shortly. Okay, this is the main instrument you'll use when flying the Delta Glider in orbital missions. But before we go through what each one of these means, I'm going to cover the next several slides, and we'll come back to this. Okay, to understand orbital mechanics requires a deep understanding of what an orbit is and how to precisely define it. Think of an orbital plane as a flat surface slicing through the Earth at a point that creates 2 equal half-spheres. One such plane is the plane slicing through Earth at the equator, dividing the Earth into the northern and southern hemispheres. This is called the equatorial plane. Another such plane could be the yellow elliptical disk right here. Okay, and objects in orbit about a central mass, say Earth, for example, would move along such planes. So you might have a satellite, or calling it here celestial body, taking this orbit, right, about Earth, which is here at the center, and this is the gray is the plane cutting through the equator of the Earth. Okay, there are 5 elements called the orbital elements, which are sufficient to completely describe the size, shape, and orientation of an orbit. These 5 elements are listed below. Okay, so A is called the semi-major axis, okay, and it refers to essentially the radius of the orbit. Okay, if it's a circular orbit, it is the radius. If it's not circular, if it's elliptical, it's just this distance here from the center to the outer part. Eccentricity provides for the shape of the orbit, right? If eccentricity equal to 0, that's a circular orbit. Greater than 0 and less than 1, then it's going to be elliptical. I is the inclination angle. So let's say the satellite is in this orbit. So the angle between this orbital plane and the plane of reference, which is the equatorial plane, is right here. See that angle I? Okay, let me make this a little bit larger. Okay, so here we have it. So that's the inclination angle, again, between the plane of reference. So this is a plane that slices through the center of the Earth, and this is the orbital plane. Um, Omega here is the longitude of the ascending node. Okay, it's the angle between the reference direction, which is the direction of the sun from Earth on the date of the vernal equinox, so in this direction here, okay, and the ascending node. Okay, the ascending node is where the plane, orbital plane, and the reference plane intersect as the object is moving in this direction. Okay, so this angle then, omega, would be from here all the way over to here. You can see it's pointed out right here. See omega here. So again, it's from the reference direction all the way to the ascending node. This is fairly complicated, and it's actually rarely used in this book. So I wouldn't really worry about it that much. Let's just move on here to more important parameters. Okay, the next angle is the argument of periapsis. It's the angle from the ascending node to the location of periapsis. Okay, so again, it's in the plane of reference of the orbital plane. So it's going to be this angle here from the ascending node. Again, that's where the orbital plane intercepts the reference plane, and it's from that location to periapsis. And I'll get to periapsis in a minute. That's just the distance of closest approach, okay, from the object orbiting and the, in this case, Earth. Another important quantity, it looks here like a V, is called the true anomaly, and it's the angle between the periapsis point and the orbit and location of the orbiting object. That's actually really important, and that's fairly simple. Okay, so this is location of the closest approach of the object, and say the object is here at this point of its orbit. This would be that angle. Okay, this is Greek symbol nu. It looks like a V. Okay, orbit geometry is important. Let's talk about it. Let's just say the delta glider, when it's closest to Earth, is here. Okay, so that would be called the periapsis point. And I've got it abbreviated R sub P. Okay, and let's say later in its orbit, it's over here. Okay, so again, as I discussed previously, the true anomaly is that angle between where the delta glider is at closest approach and where it is currently. All right. This is the distance of furthest approach, and it's called the apoapsis distance. Okay, I talked about this before. This is the semi-major axis or radius, essentially, of the orbit. And this distance here is called the semi-major axis. Okay, this is an ellipse, and Earth is located at one focal point, and there's nothing located at the other. Okay, there's several mathematical relationships that connect these values. So the periapsis point is equal to the semi-major axis times 1 minus the eccentricity. So let's say you've got the semi-major axis in the shape via the eccentricity, you can get the periapsis distance. You can get the apoapsis distance with a similar formula. It's a semi-major axis times 1 plus the eccentricity. And then the sum of the periapsis and apoapsis is equal to 2 times the semi-major axis. And that makes sense, right? If you sum this with this, you're going to get this distance here, which is 2 times this distance. Okay. This equation comes in handy as well. It's saying how far is the object in orbit from the central mass. If you know the angle, right, the angle of its orbit, you know the eccentricity and you know the periapsis point. So you can figure out where it is at any point in its orbit if you know those quantities. So here's an example. Let me reduce the size here a little bit. The eccentricity of the elliptical orbit of Mercury around the Sun is 0.206, and the semi-major axis is equal to 57.91 times 10 to the 9th meters. What is the distance between Mercury and the Sun at closest approach? So that would be the periapsis, and the furthest approach, apoapsis. Okay, so I'm going to use this equation right here. Okay, and here's my semi-major axis. I'm plugging that in. It's 57.91. Plugging that in for A. And we'll plug in that times 1 minus the eccentricity, and I get 4.59 times 10 to the 10th meters. Okay, so next is the apoapsis. I'm going to use this equation. So next is the apoapsis. I could either use this equation or I could use this equation. Okay, but I've got the periapsis, so I'm going to go ahead and use this equation. So I'm going to solve this equation for the apoapsis point, so I'm going to subtract the periapsis point from both sides. Okay, so it's going to leave me with 2 times the semi-major axis minus the periapsis point, okay, which I got from up here. And that gives me a apoapsis point of 6.99 times 10 to the 10th meters. Okay, here are several exercises that you should try. And you can check the answers by asking your teacher. The teacher will either work these out on his or her own, or they might reference my teacher's solutions manual. Okay, page 37 of the book. So I have quite a few pages where I am providing a story about something in the history of NASA. And I obtained these stories from many great books written. This is really cool. This comes from Mr. Gene Kranz's book, and Mr. Kranz helped me with my book, but he was a former NASA flight director, worked most of the Apollo missions. And I love this quote from his book. I'll go ahead and read it. I find it difficult today to convey the intense frustration and near despair as we picked ourselves up after each setback, determined to break the jinx of the program. Now we were going for back-to-back missions, launching an unmanned Atlas downrange, and then carrying out our first Redstone mission. We tried not to think about the gaps in knowledge, experience, and technology in our program. They were big enough to drive a truck through, and we could never forget that while we were screwing around with baby steps in suborbital mission, the Russians had put a man in orbit. Okay, so these early missions were really related to just getting something in orbit around the Earth. This goes back to the early 60s. And there were failures, and that's what he's talking about here, were the failures. But he hung in there. He worked at NASA for decades, and again, later, in later missions, Apollo, I think it was 11, ended up putting a man on the moon. So they never quit, and he was one of the early pioneers of the space program. Okay, next are the most important equations we'll use in flying missions to the moon and orbits around the Earth. Okay, so A comes from the law of conservation of mechanical energy. B comes from A. So this is just this equation derived for velocity. Equations C and H, so C and H come from the differential equation of motion in polar coordinates with the acceleration provided by the gravitational force. Equations D through F right here are the ellipse geometry equations. The orbital period G is Kepler's third law. It can also be derived from Newton's equations of motion. And equation I is derived from the law of cosines. It is the orbital plane change equation. So we can derive many of these equations from the differential equation of motion. This is the radial component. So this is the this component of acceleration. And this is the equation for this direction of acceleration. Okay, so in the appendix, I provide the mathematics to derive the equations of motion from these two equations. And one equation that pops out of that is this incredibly important equation, which if we know the position at burnout and the velocity at burnout, K is equal to G over G times M, two constants, right? Gravitational constant times the mass of the central object, we can get the eccentricity of the orbit. Okay, orbit energy and thrust. It says here, before continuing, please review essential physics on mechanical energy. So I'm going to go back and do that. Okay, so here we have it. The mechanical energy of an object includes energy due to its motion, just kinetic energy, and energy due to its position in the gravitational field, and that's called gravitational potential energy. So the kinetic energy of an object in motion is 1/2 times its mass times its velocity squared. The potential energy is equal to minus, this is a gravitational constant, times the mass of the central object. This is times the mass of the object orbiting the central mass. The negative value here may seem odd, but since gravitational potential energy is defined as 0 at a really far distance, so at a large r, and a really far distance is where the potential energy is at its maximum, okay, then anything less of this distance will result in a negative gravitational potential energy. Really, for analysis, the only changes in gravitational potential energy are meaningful, so the negative sign is actually kind of insignificant. Okay, so the total mechanical energy of an object of mass m in orbit about an object of mass large m is this: kinetic energy plus gravitational potential energy. Okay, and that can be shown to be equal to minus gmm over 2 times a, where a is the semi-major axis. Okay, so now you know where this equation comes from. Kinetic energy plus potential energy is equal to the energy of the orbit. So you see here that the energy of an orbit is negative, okay, unless this is equal to this, and then it becomes zero. So if the energy is zero, that means it is an open orbit. Okay, so that means it's like elliptical. So the object's going like this. It's not actually orbiting the central mass. It's like a flyby, like a comet that flies by Earth and never returns again. Okay, so that's going to be true if the kinetic energy is equal to potential energy. Again, that would be this minus this would be zero. But for the closed orbits, this will always be negative. So let's study this a little bit. As you can see here, the further the delta glider is from Earth, so the higher the R, and the faster it is moving, right? So the higher V, the higher its energy. So one must understand this equation to determine whether a prograde thrust, which recall is a thrust in the direction of travel parallel to the velocity vector, or a retrograde thrust anti-parallel to the direction of travel, should be applied when changing orbits. For example, based on this image, if the delta glider was going from orbit A here to orbit TR, would a prograde thrust or retrograde thrust be required? Okay, so you can see here, right, this is going to have a larger semi-major axis than this, making this less negative. So it's going to have less negative of energy, so it has more energy. So there's more energy in the transfer orbit than this orbit, which means you need to add energy to the orbit. And you do that by thrusting it in the direction of travel. So it's a prograde thrust. Okay, question. Which orbit has more energy? An orbit with a semi-major axis of 8 times 10 to the 6 meters, or an orbit with a semi-major axis of 7 times 10 to the 6 meters? Explain. The rocket equations provide insight into the relationship between the velocity of a rocket and the rate at which rocket fuel is burned. These equations are derived from Newton's third law, and I've done this in Appendix C. Okay, so there are two rocket equations, this one and this one. This expression tells us that the rate at which propellant is expelled from the rocket, dmdt, times the velocity of the propellant relative to the rocket, vrel, is equal to the force that the departing propellant exerts on the rocket. Okay. The product here, dmdt times v relative, is determined only by the design characteristics of the rocket engine. Okay, rocket equation number 2 is this. This is the mass of the rocket and propellant before the thrust. M sub f is the mass of the rocket propellant after the thrust. V relative is the velocity of the escaping propellant relative to the delta glider. Vi is the rocket velocity before the thrust is applied, and Vf is the velocity of the rocket after the thrust is applied. Both Vi and Vf are relative to a stationary observer. Okay, the origin of both equations comes from the conservation of linear momentum. Okay, next, orbit insight with conservation of mechanical energy. So as I explained before, this is the energy equation for an object in orbit. This is A is the semi-major axis, and that's equal to the kinetic energy plus the gravitational potential energy. So I've derived this equation from this equation. Okay, this is just a conservation of energy equation. And what it tells us is the energy at, say, a position in the orbit where it's got velocity v1 at position r1 is going to be equal in total to a position in orbit where the velocity is changed, say v2, and its position is changed to r2. Okay, doing a little bit of algebra on this, I can get from here to here. Okay, so what does this tell us about a circular orbit? Okay, this is a circular orbit. So this is the delta glider or some object in orbit, position r1, and sometime later position r2. So as you can see in a circular orbit, r1 is equal to r2. Okay, so if r1 is equal to r2, then 1 over r2 is going to be equal to 1 over r1, and their difference is going to be 0. Okay, so this side becomes 0. If this side becomes 0, that means that v2 must be equal to v1. Okay, so the speed of an object in a circular orbit is going to be constant. Okay, so applying that same equation to an object in a elliptical orbit. Okay, so let's say the delta glider is here. This is the apoapsis point. Okay, at r1, distance r1 from Earth, and at some other time, it's at the periapsis point, distance r2. Okay, so r1 is greater than r2. If that's true, then 1 over r2 is going to be greater than 1 over r1. So if 1 over r2 is greater than 1 over r1, this side of the equation is going to be positive. If this side of the equation is positive, that means that v2 must be greater than v1. So what that's telling us is that the closer an object is to that which it's orbiting, the faster it will be moving. Okay, so delta glider in this orbit will be moving faster at this point here than it will be moving at this point here. Shape of the orbit at burnout. Okay, so in the image here, the pitch angle here is the angle between the r vector, and this points from the center of the Earth to the delta glider, and the direction vector, okay, this right here, the velocity vector of the spacecraft. Okay, to the extent that is 0, okay, and in many NASA flights, that angle is 0, then the position of r sub 0, that's the position of burnout. Again, that's from the center of the Earth to the spacecraft. And the velocity of burnout, also known from the instruments, can be used to compute the eccentricity of the orbit. Additionally, for such scenario where this is 0, okay, again, the spacecraft is headed in this direction, the true anomaly is equal to 0, and the periapsis is equal to r sub 0. Okay, so from these values, all other orbital parameters can be computed: semi-major axis, apoapsis, eccentricity, etc. Okay, I'm currently in the Delta Glider spacecraft. This is the multifunction display. And what I want to demonstrate is the how to change the pitch angle. Okay, so this is the heading indicator, and it says right now the pitch angle is 0. This is plus 10 degrees. This is minus 10 degrees. Okay, so let's look outside the spacecraft. And so what does it mean to change the pitch angle? Okay, what it's going to do is I change pitch. It's going to rotate about an axis through the center here. Okay, so let's do a pitch up maneuver. Okay, there's what pitch up looks like. And let's now go pitch down. Okay. I'm going to keep it down for a while. I'm going to go back into the cockpit, and as you can see, what's happening is the angle is changing. Right now we're at 20 degrees facing down, 30 degrees facing down, 40 degrees facing down. Let's go back outside. So it's angling towards the Earth. Okay, now that's not what we want. So before you provide a thrust at the periapsis or apoapsis point, and I'll get to that in a minute, why you want to provide thrust at those points, you want to make sure that this pitch angle is equal to 0. Okay, and again, use that with the numlock pad key, 2 for pitch up and 8 for pitch down. Okay, so this is where we want to be. Pitch angle equal to 0. Okay, and bring it to right about there. All right, now let's look outside. Okay, there we are, flying level again. Orbit change, an important topic. So let's say an orbit has been established, and one mission was flown, but now another mission needs to be flown, and the orbit needs to be changed. It is possible to change the parameters of a previously established orbit, and it turns out that the best location to do this is at the periapsis or apoapsis point. Remember that the periapsis point is the point of closest approach of the orbiting object to the central mass, in this case the Earth. The apoapsis point is the distance of furthest approach. This is the multifunction display. and this represents the periapsis point. Okay, it's 6.533 million meters from the spacecraft to the center of Earth. Okay, and this is the APR, this is the apoapsis point. So on the Delta Glider spacecraft, this is the periapsis point, PER. So this is the distance from the periapsis point to the center of Earth. This is the apoapsis point, APR, distance from the furthest approach point to the center of Earth. It turns out that if a prograde thrust, and that's a thrust in the direction of travel, with a pitch angle of 0 is applied at the PER point, the periapsis point, the APR, apoapsis point, eccentricity and semi-major axis will change, but the periapsis point will not. There are good reasons why one might want to change the other orbital parameters, but keep the PER or APR points constant. A good example is an astronaut repairing a satellite. The astronaut may want the interception point of the Delta Glider and satellite to remain constant, say at the PER point, but may want to change the time of interception via modification of the semi-major axis of the Delta Glider, which can be done via thrust at the PER point. Okay, here's an example. Assume you are piloting the Delta Glider and the orbital parameters are given by the orbit MFD here on the right. Assume that you provide a thrust at the PER point. Compute the delta V to take the eccentricity from the Delta Glider MK4 in orbit, value of eccentricity of 0.0297. Okay, that's where it is currently. And we want to change this to an eccentricity value of 0.25. A delta V is just the change in velocity. Okay, the current velocity is 7927 K, that's 1,000, so 7927 meters per second. Okay. And we want to take that to a value which will give us this new orbit. Okay, here's the way to do that. So using the energy equation, which was previously introduced, I solved that equation for the velocity. Okay, and I'm also going to use this equation here, which relates the periapsis point to the semi-major axis and the eccentricity. Okay, first thing I'm going to do is use this equation to compute the new semi-major axis of the orbit, which will give me this eccentricity of 0.25. Okay, so I'm going to enter the current periapsis point, because that's not going to change, because that's where I'm going to provide the thrust. Okay, if we go up here, we can see that's 6.533 million meters. So 6.533 times 10 to the 6th is equal to an unknown value of the semi-major axis times 1 minus the eccentricity. Okay, this is one equation I want to know, and I can solve for A. And that turns out to be 8.71 times 10 to the 6th meters. Okay. Now I plug that into the velocity equation to get the new velocity. Okay. So this is the current location. R is the current location of the thrust. Again, we're providing the thrust at the periapsis point. And this is the semi-major axis. So 2 times this value here. And then, of course, this is just the mass of this, what we're orbiting. This is Earth in this case. And G is always the same, 6.67 times 10 to the minus 11. Okay, so solving this equation gives us a velocity of 8736 meters per second. Okay, so this is the new required velocity that must be realized at the point of thrust. Okay, now because we're entering into a non-circular orbit, the velocity as the Delta Glider goes about the Earth is going to change. Okay, but that's not important. Important thing is to get the delta V correct. Okay, so again, the delta V is the difference between the current velocity and the final velocity after thrust. It's computed as follows. We've got the new velocity, 8736, and then we got the previous velocity, 7927. So we need a delta V of 809 meters per second. Okay, so why is the delta V so important? Why do astronauts always talk about it? Well, from the delta V, the required thrust duration can be computed using the impulse momentum theorem. F in this equation down here is the thrust. The maximum thrust on the spacecraft is 320,000 newtons. Okay, so from this equation, right, and the delta V, right, this is the delta V. Factor M out, and you're going to get M times the delta V. We can find out the duration of the thrust. So that's important. How long do we need to thrust it for at 320,000 max? Okay, so try these exercises. Okay, the Holman transfer method. This is actually a really important maneuver that in this class we will execute for a mission to the moon. It's also executed by NASA when they go from the Earth to Mars. Okay, and that's what this diagram is all about. But let me just first talk about what a Hohmann transfer is in general. It's considered the most energy efficient method for transferring a spacecraft between two circular orbits. The method involves two impulses to take the spacecraft from a circular parking orbit, say around the Earth, for example, to an elliptical orbit, and two, an impulse to take the spacecraft from the transfer orbit to a circular parking orbit about the destination planet or moon. Prior to executing the impulses, the spacecraft must be on the same orbital plane as the destination planet or moon. And I'll show you more about what that's all about here shortly. Additionally, to achieve the energy savings benefit, the transfer orbit's ellipse must be tangent to both the initial and final circular orbits at the transfer orbit's perigee and apogee, respectively. One drawback of using the Hohmann transfer method is that alignment of the Earth and destination planet must be such that the above can occur. Okay, so for a mission from Earth to Mars, this means that the Earth must be at opposition to Mars, which only occurs every 26 months. For a mission to Mars, which can be executed on the DG in Orbiter 2016, the delta V at position A would be in the direction of travel, and at position B in the direction opposite to that of travel. Okay, so I'm referring to this diagram here. So you want to go from Earth to the moon. Let's say here's your spacecraft. Well, we're already in a circular orbit, approximately about the sun. So you would fire prograde thrust at this point here, okay, and enter into an elliptical transfer orbit. This orbit is still about the sun, okay, but the idea is once the spacecraft is here, Mars is here, okay, and then at such point, a retrograde thrust, so a thrust in the direction opposite to that of travel, is fired, and this transfer orbit is reduced to a circular orbit about Mars. And then the spacecraft orbits Mars for the number of days required for the mission. And when the mission is completed, fires thrust to, again, engage in the elliptical transfer orbit back to Earth. I'll show you an example of this in a bit here that's related to the mission to the moon. Okay, page 63, Physics for Space Travel. This has to do with a maneuver to confirm certain laws of physics. This maneuver will enable you to confirm Newton's second law with the Delta glider. Here are the instructions for doing that, okay, and here is the exercise. So you're going to confirm, this is going to be the average force or thrust, right? Thrust is a force. Is equal to the average mass. Of course, as you're burning fuel, the mass of the Delta glider is changing, but it doesn't change that much for a pretty short burn, times the average acceleration. And of course, average acceleration is the change in the velocity over the change in the time. Okay, so the scenario that I ran when I wrote the book was initial mass of the Delta glider of 18,204. The initial velocity before I applied the thrust was 7,915. The final velocity was 9,951. This is pretty arbitrary. And it took 125 seconds to get from here to here. Okay, so when I computed this, I ended up with 296,506 newtons. Okay, the actual thrust applied was 320,000 newtons. The difference is due to the fact that it takes a little time once full thrust is applied for the thrust on a Delta glider to reach 320,000 newtons. Okay, so you try it. Here's an exercise. You'll start from approximately 7915 meters per second as soon as you enter into the simulation. But I want you to take it to 8,500 meters per second and recall the velocity is here on the multifunction display in the cockpit. And then measure the time it takes to get to this 8,500 from wherever you start. Okay, and you'll use the quote-unquote SIM timer, top right-hand corner of the screen, to look at the time difference between when you started and when you ended up at 8,500. You'll plug all those numbers into this equation, and it should come out pretty close to 300,000 or something like that. Okay, so give that a go. Okay, so you'll see the Orbiter 2016 should be here on your screen. Go ahead and double click that. You're going to go into the Delta Glider folder, select the DG MK4 in orbit. Okay, so here's your cockpit. Go ahead and hit the F8 key to select. This is probably the easiest cockpit to work with. You want to put the spacecraft into prograde position. It's going to be a prograde thrust, so it's going to rotate a bit. Okay, and then just orient yourself to the keyboard. Look at the control key and the plus key. That's going to be a positive thrust. You're going to go to 320,000 newtons, and then you'll hit Control minus to shut it off. Okay, so go ahead and create your scenario, F equal ma. Okay, and you want to compute a V final minus V initial over the time change. Okay, here's your timer. So before you provide the thrust, make a note of the time. When you're done thrusting, make a note of the time again. You're going to take that difference. That's going to be your change in time. And then, of course, you're going to start with an initial velocity. Let's go ahead and start it at 7913. This changes a bit because it's not a perfectly circular orbit. 7913 is a good number. That's your initial velocity. And then your final velocity is shoot for 8,500. If it's a little more or a little less, that's okay. Just make a note of the time it took to get there. Okay. All right, so I'm going to do that now. So the time, I'm going to write down the time of time initial. Let's say 100 seconds. It's about when okay, I'm going to hit Control plus. And if you look at the thrust, the main engine thrust, it's going to 320,000. Okay, so here it is right here, 320,000. And then when it gets to about 8,500, we'll shut it off and make a note of the time, and then we'll compute the force. Here's information. So you can look at the total mass of the spacecraft. So go ahead and use 18,673 as your total mass. Okay, and we can go ahead and shut off the thrust. We're actually a little bit above 8,500. Okay, so we're at 8582 at about 150 seconds. 8582. Actually, it's a little bit less. Yeah, 100. Let's just call it 145 seconds final time. 145 seconds. Okay, so you have the final velocity of 8582, or I do. My scenario, 8582. Initial velocity was 7913. And it went from 100 seconds to 145 seconds. So about 45 seconds was the thrust duration. And I'll go ahead and multiply that by the total mass here, right, of the craft. Okay, so that changed a little bit as we thrusted, but 18,673 is fine. In the book, it's a lesser number because I'd been flying other missions at the time, but it doesn't really matter. So 18,673. Okay. Those are my numbers. And but I want you to generate your own numbers, and you should get 320,000 thrust. It's going to be a little bit less than that, but go ahead and give it a go. Okay, page 71, torquing the Delta Glider. So many times you need to rotate the Delta Glider, and the way you do that is via a torque. Okay, so a torque results in an angular acceleration, alpha. I is the moment of inertia, and that's how the mass is distributed around the rotation point. The rotation point for something in space is going to be its center of mass. So next I'm going to apply this equation to torquing the Delta Glider. So the R is the distance from the point where the thrust is being applied to the point of rotation, which is the center of gravity. F is the thrust. And the angle here is the angle between the R vector and the F vector. Okay. The actual location of the thrust is a little bit more this way, but I decided to simplify and just go here. So the angle, therefore, is 90 degrees. So the torque due to this thrust is just going to be R times F. Okay, so when you fire rotational thrusters, you get two different jets. So one jet goes this way, right? The gas goes that way, and the thrust goes that way. For this one, the gas goes this way, and the thrust goes that way. But they both contribute to rotate this thing in a counterclockwise direction. Okay, so in this equation, here's the R, right, from center of mass to the point where the thrust is being applied, and here's the F, here's the force. You've got a little bit of an angle here, right? But let's just say it might be 10 degrees, so not much. This would be sine of 10 degrees times this r vector times the thrust. Let's see what that looks like on the simulator. I'm going to load the Orbiter 2016. Going to go to the Delta Glider, DGMK4 in orbit. Okay, I'm going to go to my favorite cockpit, so using the F8 key, there it is. I'm going to turn on rotational thrusters, there we go. Okay, and look at the velocity. Okay, the velocity is 7918. Rotation will not cause the linear velocity to change. Okay, so let's go outside here. Okay, and I'm going to hit the 1 key on the numlock pad. Okay, you should see thrust come out here and also here. So there it is. Okay, so the gas is going this way, the thrust is going this way. It's causing the whole thing to rotate about its center of gravity. So let's look at this one down here. Okay, the gas is going that way, the thrust is going that way, or the force is going that way. Again, it's contributing. Both ends are contributing to the orbit or the rotation in the same direction, which, looking up here from the top is counterclockwise. All right, and let's see if the velocity changed. Let's go back into the cockpit. And yeah, you can see the velocity did not change. It's going to be right around 7914, 15, 16. It changes a little bit because the orbit's not perfectly circular. Okay, so there you have it. And then once you've rotated to the angle of interest, you go ahead and you hit kill rotation. All right. So now the motors are angled quite differently than before. So providing a thrust in this direction, right, is going to result in quite a bit different orbital trajectory. Okay, page 74 of the book. This is actually very important. You have to speed up to slow down in orbit. And so what that means is if you go to, say, the periapsis location and provide a thrust, you're going to see that the velocity will increase. And if you look at the orbit MFDs right here, this was a velocity 7925 meters per second before a thrust. And here you'll see that this is the velocity after the thrust. The velocity has gone up to 8181 meters per second. And you can see the semi-major axis has also increased from 6.733 to 7.234. And we know that an increase in the semi-major axis will result in a higher energy orbit. And also you can see that it's obviously a much larger orbit. Okay, so this has got a higher energy than this, but the average velocity of this orbit is less than this orbit. So that might seem counterintuitive because you're looking here that the instantaneous velocity has increased. So I want you to prove that to yourself. I want you to go ahead and compute this value right here. The average velocity is equal to the circumference of the orbit divided by the period of the orbit. And those can be computed with these equations. A is a semi-major axis. B is a semi-minor axis. That's SMA and SMI. M is the mass of the Earth, whatever one is orbiting. Again, in this case, the Earth. So that's 5.98 times 10 to the 24th. G is the usual 6.67 times 10 to the minus 11th. Okay, so compute this for before thrust and after thrust, and you'll find that this is proven. You're going to speed up, right? But that's actually going to slow your average velocity down. It's a very important idea when you're timing the interception of a satellite for a satellite repair in orbit. Okay, page 76 of the book, verify conservation of mechanical energy. Gravity is a conservative force. This means that the total mechanical energy or specific mechanical energy of the DG as it orbits the Earth will be constant. Mechanical energy is the sum of kinetic and potential energy. Previously, I showed you that the energy equation is 1/2 mv squared minus gm little m over r1. If we divide both sides by the mass of whatever's flying, in this case the Delta Glider, that equation turns out to be this. This is energy per unit mass And the reason this is more efficient is because you don't have to worry about what's the mass of what is flying. Okay. But anyway, if you go ahead and compute this at one location, R1, at its velocity V1 in orbit, and then wait some time later and compute it again at some different velocity V2 at some different location R2, you'll find that these energies are equal. So this is a really important idea to verify. Energy is conserved. Okay, so I've provided an exercise for readers to try, and it's fairly simple. So go to the DG MK4 in orbit scenario um, and create an eccentric orbit. Okay, the default orbit is too circular. Okay, so the R's and the V's stay pretty much the same. But in an eccentric orbit, the R's and the V's change. Okay, so again, create an eccentric orbit, eccentricity greater than 0.25, but make sure it's less than 1, because if it's 1, then it's no longer in orbit. The next thing you want to do is just go to one position in that orbit and write down the R vector. Okay, it's RAD on the instruments. Write down the V, the velocity. Okay, that's just VEL on the orbit MFD, and then compute this equation here. Okay, the mass of the Earth, M, is 5.98 times 10 to the 24th. The gravitational constant, G, is 6.67 times 10 to the minus 11th. Okay, and go ahead and put down the angle, TRA, right? That's just the angle relative to the periapsis point. Okay, and then time travel with the T and R keys, not too much, just go to 100 times, so that you're quite a bit away from position 1. And then do the same thing. Write down the R vector, the velocity vector, the magnitude of it, and compute the specific energy again. And you should find that they're equal.